Swayam Prabha. Digital India. Educated India.
Now we are going to discuss latent variable perspective. So in the previous section we derived PCA, principal component analysis, without any notion of probabilistic model, using the maximum variance and projection perspectives. On the other hand, this approach may be appealing as it allows us to sidestep all the mathematical difficulties that come with the probability theory, but on the other hand the probabilistic model would offer us more flexibility and useful insights. And more specifically, the probabilistic model would one come with the likelihood function, and we can explicitly deal with the noisy observation which we did not even discuss earlier. And next is allow us to do Bayesian model comparison through the marginal likelihood as discussed in section, and view of principal component analysis as a generative model which allow us to simulate new data. So further notice, allow us to make straightforward connection to related algorithm and deal with the data dimensions and are missing at random by applying Bayes theorem, and give us a notation of novelty of the new data point. So further we have a point, give us a principled way to extend the model, like the mixture of principal component analysis. Have a PCA we derived in earlier section as a special case. Allow for the fully Bayesian treatment for marginalizing out the model parameter. So by introducing continuous valued latent variable z in r power m, it is possible the phrase PCA as a probabilistic latent variable model. So Tipping and Bishop proposed this latent variable model as a probabilistic PCA, probabilistic principal component analysis, addresses most of the aforementioned issues, and the PCA solution that we obtained by maximizing the variance in the projected space or the minimizing the reconstruction error is obtained as a special case of maximum likelihood estimation in a noise free setting. Next, generative process and the probabilistic model. In the probabilistic principal component analysis, we explicitly write down the probabilistic model for linear dimensional reduction. For this we assume a continuous latent variable z belongs to r power m in m tuple. The standard normal prior p of z is equal to noisy of 0 comma I, and the linear relationship between the latent variable and the observed x data, where x equal to bz plus mu plus epsilon in r power d, where epsilon in n of 0 comma sigma square I is a Gaussian observation noise, and b belongs to r power d cross m, and mu belongs to r power d, describe the linear affine mapping from latent to observed variable. Therefore, the probabilistic principal common analysis links latent observed variable as through probability of x over z comma b comma mu comma sigma square equal to noisy of x by bz plus mu comma sigma square I is a Gaussian observation. So overall the probabilistic principal component analysis induces the following generative process Zn is equivalent to n of z by o 0 comma I, and xn by Zn is equivalent to n of x by b Zn plus mu comma sigma square I. So, to generate a data point that is a typical given the model parameters, we follow an ancestral sampling scheme. So, we first sample a latent variable Zn from P of Z, then we use the Zn in 64 to sample a data point condition on a sampled Zn, where xn is equivalent to P of x by Zn comma b comma mu comma sigma square. So, this is the probabilistic model using the joint distribution of a random variable, and the generative process allows us to write down the probabilistic model of probability of x comma z by mu b comma mu comma sigma square equal to probability of x by z b mu sigma square of P of z, which immediately gives rise to the graphical model in the figure. The figure says that graphical model for probabilistic principal component analysis. So, we have an observation xn, and explicitly it depends on the corresponding latent variable, and b mu sigma square, right, mean and standard deviation and variance. So, b and mu are likelihood parameter and sigma are the shared across the data set, and corresponding the Zn is a sample data, and with the sampled condition and is equivalent to this probabilistic model. Now, we have a note. So, we have generating the new MINIST digits, the latent variable of Z, and the direction of arrow that connects the latent variable and observed data. So, the arrow point from Z to X, which means that probability principal components analysis model assumes a lower dimensional latent cos Z for high dimensional observation X. In the end, we are obviously interested in finding something out about Z given some observation, and we apply the Bayesian inference to invert the arrow implicity and go from observation to latent variable. So, this is the generating of a new data latent variable, and we stay to the training the data, the more realistic generated data. So, this figure shows the latent coordinates of a MNIST digit 8 found in the principal component analysis when using a two-dimensional principal subspace blue dot. We can query any vector z star in the latent space and generate the image x star is equal to b z star that resembles the digit 8. So, we show 8 of such generation images with the corresponding latent space representation. So, it depends on where we query the latent space, and generate the images look different. So, we query away from the training data and more artifaces. For example, the top left and the top right digits, note that the intrinsic dimensionality of these generated images is only 2. Now, we are going to discuss the likelihood and joint distribution. So, using the result from the previous ideas, we obtain the likelihood of the probabilistic model by integrating out the latent variable Z. Therefore, probability of x by b comma mu comma sigma square is integral probability of x by z b mu sigma square into P of z dz. So, this resultant is noise of Gaussian distribution x by b z plus mu comma sigma square I into n of z by 0 comma I into dz. So, this is the solution of this integral is a Gaussian distribution with a mean expectation of x equal to E of b z plus mu by base z plus expectation of epsilon base E equal to mu, with the covariance V of x equal to V of z of Bz plus mu plus V epsilon of epsilon equal to Vz of Bz plus sigma square I. So, B is a constant, take it outside, then B into Vz of z is B into B transpose plus sigma square I, which is equal to BB transpose plus sigma square I. So, in the equation 68B can be used for the maximum likelihood, or we can denote MAP, estimation of the model parameter. So, we have a note. So, we cannot use the conditional distribution in the equation 64 or maximum likelihood estimation, as it still depends on the latent variable. So, the likelihood function we require for maximum likelihood estimation should only be a function of data x and model parameters, but must not depend on the latent variables. So, from this section we know that the Gaussian random variable z and linear affine transformation x equal to Bz of it are jointly Gaussian distributed. So, we already know the marginal P of z equal to noisy of z comma z base 0 of I is a Gaussian. P of x equal to x by mu comma BB transpose plus sigma square I, and using this cross covariance is given by covariance of x comma z equal to covariance of Bz plus mu base z equal to B into covariance of z comma z equal to B. Therefore, the probabilistic model of probabilistic principal component analysis is a joint distribution of a latent and observed random variable is explicitly given by P of x by z by B comma mu comma sigma square equal to n of x comma z into mu of mu comma 0 and corresponding BB transpose plus sigma square BEI and B transpose I. It means the vector of a length D plus m and covariance matrix of the size D plus m cross D plus m. Next, posterior distribution. The joint Gaussian distribution P of x z by B comma mu comma sigma square allow us to determine the posterior distribution. So, P of z by x is immediately by applying the Gaussian condition. So, the posterior distribution of the latent variable given an observation of x is P of z by x equal to n of z by m comma c, where m equal to B transpose of BBV transpose plus sigma square I whole inverse into x minus mu, and c equal to I minus B transpose of BB transpose plus sigma square I into whole inverse B. So, note that the posterior covariance does not depend on the observed data x. For the new observation x star in the data space, we use equation 73 to determine the posterior distribution of the corresponding latent variable z star. So, the covariance matrix C allows us to assess how confident and the embedding is. So, your covariance C with a small determinant which measures volume tells us that the latent embedding z star is fairly certain. So, if we obtain a posterior distribution P of z bar z by x with much variance, so we may faced with an outliner. However, we can explore this posterior distribution to understand what other data points x are plausible under this posterior. To do this, we exploit the generative process underlying the probabilistic principal component analysis, which allow us to explore the posterior distribution on the latent variables by generating new data that is plausible under this posterior. So, we have two cases. Sample a latent z star is equivalent to P of z by x star from the posterior distribution over the latent variable. Number 2, sample a reconstructed vector x star is equivalent to P of x by z star B comma mu comma sigma square. So, we repeat this process many times, we can explore the posterior distribution on the latent variable Z star and its implication on the observed data. So, the sampling process effectively hypothesis data which is plausible under the posterior distribution. Let us start with an example, the coin toss of example. Say you toss a coin n times. So, we have to taken from the net some more example in the ideas. Therefore, we say toss a coin n times, you want to figure out its bias. So, Bayesian approach, find the generative model, each toss is approximately equal to Bernoulli theta and theta is approximately beta of alpha comma beta. So, draw the generative model in the plate notation. So, this is the picture where we already discussed with two variable alpha comma beta is approached to theta and it is tossed with corresponding to beta of this. So, beta of alpha comma beta, we have a generative model in the plate, and next one is a plate notation and random variable as a circle and parameter fixed values as a squares and a repetition of conditional probability structure as a rectangle plates and a switch condition as a squiggles and random variable observed in practice are shaded. So, next we have a generative model, and I have already looked at the generative model for supervised learning. So, generative models are even more common popular for unsupervised learning like clustering, dimensionality reduction, probability density estimation. So, in such a model each data point is associated with a latent variable. So, clustering mean the cluster is in ID Zn which is a discrete or a k dimension, one hot or repetitive or a vector of a cluster membership possibilities. Another one is a dimensional reduction, the low dimension representation Zn in R power k. So, these latent variable will be treated as a random variable and not just for their unknown. We will therefore assume a suitable prior distribution on this estimation of their random variable. If we need a point estimation of these latent variable, that can be done too. So, this is the mapping from Zn to Xn, and the latent variable Zn usually encode some latent properties of the observation Xn. So, we have taken from the net generative model with the latent variable, and I acknowledge that IIT Kanpur, that is introduction to ML is given, and this typical generative model with the latent variable might look like this, phi of Zn to Xn, and in this generative model the observation Xn assume generated via latent variable Zn. Therefore, the unknown is such a latent variable model LVM are of the two types. One is global variable and shared by all data, a point of theta and phi in the above diagram. So, this need a probability distribution on both, and phi of Zn by phi is a suitable distribution based on the nature of Zn, and phi of Xn by Zn is a suitable distribution based on the nature of Xn, and then this local variable is specific to each data of Zn in the above diagram, and note both global and local unknowns can be treated as a random variable. So, however, here we will only treat the local variable Zn as a random latent variable and regard theta and phi as other unknown parameters of the model. So, as an example of a generative LVM is probabilistic clustering can be formulated as a generative latent variable model. Assume k probability distribution 1 for each cluster, and in any such LVM we phi denote the parameter of the prior distribution of Zn and theta denotes a parameter of likelihood distribution on Xn. So, this is a mapping phi of Zn to Xn, and then we have a discrete latent variable with k possible or one hot vector of length k modeled by multinomial distribution as a prior. So, this is xn is generated from one of the k distribution depend on the true value of Zn, which clustering will find, and this should be the likelihood distribution, and phi, the function denotes the parameter vector pi equal to pi 1, pi 2 and so on of the multinomial distribution, and phi of Zn by phi is a multinomial of pi. So, this means phi of Zn equal to k by phi equal to phi k, and theta is a parameter of k distribution. Example, theta equal to mu k and summation k, where k varies from 1 to k, and p of xn by Zn equal to k comma theta equal to n of mu k comma summation k. So, this is the corresponding picture of n of x by mu comma epsilon and n of x by mu 2 epsilon 2 and n of x by mu 3 of epsilon 3 and corresponding probability distribution function. So, this is probabilistic clustering, and this p of x is a Gaussian mixture model of GMM. Next, parameter estimation for generative LVM. So, how do we estimate the parameter of the generative LVM, say probability clustering? So, the guess about Zn can be in one of the two forms: a hard guess, a fixed value, some optimal value of the random variable Zn, and the expected value E of Zn of the random variable is Zn. So, using the hard guess of Zn will result ALT opt-like algorithm, and using the expected value of Zn will give the so called expectation maximization. So, we have a function like this. So, corresponding EM is perfect, but this is width of the latent, and the next one is a parameter estimation for generative LVM. So, can we estimate the parameter theta comma phi equal to capital theta, say the LVM without estimating Zn? If we say the principle is yes, but it is a harder. So, given n observation xn, where n varies from 1 to n, is a MLE problem of theta will be, the decision here is also true for map estimation of theta. Therefore, the argument of max is equal to summation n equal to 1 to n log of p of xn by theta, and the argument of max is equal to n equal to 1 to n log of p of xn comma Zn bar theta. Therefore, the summing over all possible values of Zn can take would be integral instead of sum of Zn is continuous. So, for the probabilistic clustering model, we say that p of xn by theta will be the decision here is also true for map estimation of theta. Also note that p of xn comma Zn equal to p of Zn by phi of xn by Zn theta, and here log of p of xn by theta is a summation integral over on the RHS, and it is no longer exponential family even if phi of Zn by phi and phi of xn by Zn phi are in exponential form. And this probabilistic clustering model, we say p of xn by theta will be p of xn by theta equal to summation k equal to 1 to k p of xn comma Zn equal to k of theta, and where k varies from 1 to k, p of xn equal to k by phi of xn by Zn equal to k of theta, and which is equal to k equal to 1 to k of pi k of n of xn by mu k of summation k. So, the MLE problem thus will be a convex combination of the mixture of k Gaussian. It is no longer an exponential family distribution, and this MLP problem will be argument of maximum of summation n equal to 1 to n log of k equal to 1 to k pi k of n of xn by mu k comma summation k. So, once again thanks to IIT Kanpur and the introduction of ML, they given the sharing this slide is a very good problem, and I acknowledge this to the IIT Kanpur that the log of sum does not give us the sample expression, So, MLE can still be done using the gradient based method, but update will be complicated. So, the ALT opt or EM make it simpler by using the guesses of Zns. So, another example of generalized LVM is a probabilistic principal component analysis, another example of generative latent variable model. Assume k dimensional latent variable Zn mapped to d dimensional observation through probability mapping, and this is a function phi such that Zn to xn of theta, where probabilistic principal component analysis has several benefits over PCA, some of which is include can use suitable distribution of xn to better capture properties of data, and another one is parameter estimation can be done faster without eigen decomposition. So, the real valued vector of the length k model by a 0 mean k dimensional Gaussian distribution as a prior, and phi of Zn by phi equal to n of 0 comma ik, and the parameter of the Gaussian prior on Zn in this example, no such parameters are actually needed since mean is 0 and covariance of matrix is identity, but can use non-zero mean and more general covariance matrix for the Gaussian prior. So, here theta is a parameter defining the projection from Zn to xn, and here mu mean of W equal to Z, W into Zn is a k cross 1 matrix, and W is a d cross k mapping, and mu n is a d cross 1 because d cross k into k cross 1 is d cross 1 mean of the mapping. Therefore, the probability PCA can be P of xn by Z1 equal to W of sigma square equal to n of mu n comma sigma square ID. So, this is the probabilistic mapping, means that will be not exactly, but somewhere around the mean. Therefore, xn equal to W Zn plus epsilon n. So, this is a Gaussian noised just like a probabilistic ideas. So, also instead of the linear mapping WZN to xn mapping can be defined a nonlinear mapping, and PPCA has several benefits over PCA, some of which include, and it can be suitable distribution for xn to better capture properties of data, and parameter estimation can be done faster without eigen decomposition. So, if Zn were known, it just become a probabilistic version of the multi-output regression problem, where Zn in r power k are the observed input feature and xn in r power k are vector valued outputs. Generative models and generative stories. So, data generation for the generative model can be imagined through generative story. The story is just our hypothesis of how nature generated the data. And next point is for the Gaussian mixture model, the somewhat boring story is as follows. That is, for each data point xn with index n equal to 1 to n, and generate its cluster assignment by drawing from prior P of Zn by phi. Assuming Zn equal to k, generate the data point xn from P of xn by Zn comma theta. So, Zn is equivalent to multinomial pi. So, xn is equivalent to n of mu of k comma summation k. So, it can be imagined a similar story for PPCA with Zn generated from n of 0 comma ik and then condition on Zn. So, the observation xn generated from P of xn by Zn W comma sigma square equal to n of W Zn comma sigma square ID. So, for GMM PPCA the story is rather simplistic, but for more sophisticated model gives an easy way to understand, explain the model and data generation process. So, this taken from the internet and introduced by the IIT Kanpur by the introduction of ML, and this is the most important point we have taken. So, it is not in the normal textbook, then it is a very good analysis we taken from these ideas.